Good morning, everyone. I'm Akira Shimada, CEO of NTT. Thank you very much for joining us today at the NTT's R&D Forum 2025. I'd like to speak to you under the theme of innovation in computing powered by photonics technologies. Today, I will introduce two major computing innovation enabled by NTT's photonic technologies. The first is ion photonic computing. By replacing electrical wiring with optical wiring, we break through energy limitations and enable a low-power computing infrastructure for the AI era. The second is optical quantum computer. This technology surpasses the computational limit of conventional computers and solve previously intractable problems with dramatically lower power consumption. First, let me introduce the first innovation, ion photonic computing. Please watch the video.
NTT aims to support the evolving communications of the future with low power consumption through light, with its ion photonic disaggregated computing, from both the hardware and software perspectives. In terms of hardware, electrical signals will be replaced with optical signals, reducing power consumption and achieving high-speed communication with low latency. In terms of software, large-scale computers that require advanced processing have traditionally had restrictions on the combination of parts, necessitating the installation of additional cabinets, which consumed power even for parts that were not being used. However, by removing these restrictions and using resource allocation technology that allows only the necessary functions to be used in the amounts required, we have achieved more advanced processing and reduced power consumption. In the future, by combining this with the ultra-high-speed APN network, it will be possible to utilize computers in remote locations as if they were a single high-performance computer. This will enable efficient use of electricity near renewable energy sources and power generation facilities. Through these technologies, NTT will support the evolving communications of the future with low power consumption through light.
Now that you have seen the video, let me explain the background behind NTT's focus on ion photonic computing. As you know, AI utilization is expanding at an unprecedented pace. It once took Facebook 44 months to reach 100 million users. But the OpenAI ChatGPT reached the same milestone in just 2 months. With this rapid expansion, the global AI market is projected to grow to $1.8 trillion by 2030. The scale of the computing used to develop and operate AI model is growing at a rate of about 1.8 times per year. In 2020, OpenAI ChatGPT-3 system was equipped with roughly 10,000 GPUs. By 2022, the GPT-4 system, 200,000 GPUs. In AI system with a large number of GPUs, enormous volume of data must be exchanged between GPUs. As a result, inter-GPU communication bandwidth has grown sharply. NVIDIA's latest GPU support communication speed of 14.4 terabit per second. This is equivalent to transferring the data of 72 Blu-ray movies in 1 second. In such high bandwidth environment, electrical wiring becomes significantly less efficient as the transmission distance increases. With today's massive data flows, even short connection of only a few tens of centimeters inside a computer can consume substantial power. In contrast, optical communication consumes almost no additional power, even over longer distances. This is the advantage of light. Because of these differences, communication inside computers are reaching the limit of electrical wiring. This chart shows the regions where electrical and optical communications are suitable. As communication bandwidth increases, even short distance requires optical communications. In the ultra-high bandwidth communications required by today's AI systems, we are clearly reaching the limit of electrical communications, and optical technologies are becoming more suitable options. For more than 40 years, NTT has advanced research, development, and deployment of optical communication technologies, supporting the evolution of information networks. We began by connecting NTT central stations with optical links to achieve large capacity and higher speed. Over time, we extended optical communications to home and inside data centers. We have continuously innovated optical communications to meet the most advanced need for each era. Next, I will outline how our optical communication research and commercialization have evolved along this path. Currently, most components inside computers, such as CPUs and GPUs, operate only on electricity. These components are interconnected by electrical wiring. However, as mentioned earlier, even over a short distance, transmitting large volume of data required significant electrical power. By replacing these electrical links with optical ones, we can substantially reduce power consumption. However, simply replacing electrical wiring with optical wiring is not enough. Since processing components operate on electricity, signals must be converted between electrical and optical forms. So we need compact and efficient devices for this conversion. These are what we call photonics electronics convergence, PEC devices. So what exactly are PEC devices? These are integrated packages containing all the functions needed to convert a signal between light and electricity. To realize photonic computing, each component inside the computer will require one of these devices. This requires making the devices as small as possible and maximizing its power efficiency to avoid unnecessary energy consumption. Under the ION version, we plan to enhance PEC devices in stages and extend their application from the network down into computer itself. In ION 1.0, we applied our first generation device, PEC-1, to network interconnects such as relay equipment, data center interconnects, and server-to-server links. As a resulting high-speed, large capacity, low latency network service, APN ION 1.0 was commercialized in 2023. With ION 2.0, which began in 2025, we are finally applying these devices inside computers. Using the evolved PEC-2, we are replacing electrical wiring between computer boards with optical wiring. In the following section, I will show you what ION 2.0 looks like now that it has moved into the realization phase. The equipment shown here is a system we have developing to deliver ION 2.0 with commercial availability planned for fiscal year 2026. On the top left is a PEC2 device. It's a very compact device and is also referred to as an optical engine. The optical communication switch below incorporates 16 PEC2 devices and can transmit 102.4 terabit per second and offers performing fully suited for AI workloads. We demonstrated the computer operating at the 1/8 the power consumption at the NTT Pavilion at the Osaka Kansai Expo this year. Then what makes the PEC switch superior? In conventional optical communication switches, optical modules were inserted at the front of the switch and connected via electrical wiring to the IC tips that perform switching and control. At roughly 300 millimeters, this long electrical run was a major contributor to increased power consumption. In the new switch, the optical engine and the IC tips are mounted together on the single baseboard, allowing optical wiring to be routed much closer to the processing logic. As a result, we have been able to reduce the length of electrical wiring by roughly a factor of 10 to around 30 millimeters and dramatically lower power consumption. To bring this PEC switch to market, we have established partnerships across the global supply chain, including with Broadcom in the United States and Acton Technologies in Taiwan. With our group, NTT Innovative Device serves as a design and manufacturing hub for the core optical engine and switch module, and also coordinate the overall system integration. Some may wonder if such high capacity capability is necessary. This chart shows the processing capacity of Broadcom's Tomahawk LSIs, which is used in the data center switches. Tomahawk 6, the latest model as of 2025, already processes 102 terabit per second, confirming the need for optical wiring. NTT Innovative Devices is currently building production capability of 5,000 optical engines per month per manufacturing line. Going forward, we plan to expand to at least 3 lines developed depending on the demand. To enhance productivity, we are producing advanced automation, such as robotic assembly, into the assembly, packaging, and inspection processes. Now, I'd like to turn to our technology development and ION next phase, ION 3.0. In ION 3.0, we will move beyond the board-level optical connections, introducing in ION 2.0 and using the next generation PEC3 device, a transition to optical connectivity directly between semiconductor packages such as CPUs and GPUs. In ION 3.0, we will achieve dramatic power saving by transmitting information directly from packages via optical wiring. To achieve this, it is necessary to shrink the PEC device to a size that can be directly attached to the package. To that end, NTT has fundamentally reinvented the structure of optical devices, developing a proprietary thin film fabrication method known as a membrane device architecture. To prototype optical transmitter module, mount 16 of these membrane devices onto the extremely compact chiplet small enough to rest the tip of finger. We are accelerating research and development on this APEX-3 optical chiplet as we move toward commercialization. We expect to begin offering commercial sample in 2028. A prototype of optical chiplet under development is on the display at this event, and we encourage you to take a look. IOWN will continue to evolve even after 3.0, with IOWN 4.0 targeted for around 2032. We will begin optical interconnection inside the package itself, ultimately aiming for a 100-fold reduction in power consumption. I will represent more than 40 years of NTT's optical R&D. This body of innovation is now expanding beyond traditional telecommunication into the very heart of computing. Next, I'd like to introduce the second major innovation enabled by photonic technologies, the optical quantum computer. Please watch this video.
最新のコンピュータや AI 技術でも解決が難しい問題に対し、量子コンピュータの期待が高まっています。量子コンピュータの研究は近年急速に進展し、産業化の波が押し寄せています。市場予測では2030年代には数兆円規模に成長。期待はかつてないほど高まっています。量子コンピュータには超電導、中性原子、光などさまざまな方式があります。NTT は光通信技術から生まれた光量子方式に挑戦。光の特性を生かすことで高速・省電力で圧倒的なスケーラビリティを実現。通信との親和性も高く、未来のネットワークとつながる力を持っています。私たちは光の力で量子計算を次のステージへ導きます。それはエネルギー効率を極限まで高めた持続可能な社会の新しい計算基盤です。
I'm sorry, this video is very new, and I'm sorry in Japanese. And next time we change into the English version. Now that you have seen that video, let me explain the background behind the growing need for quantum computing. Conventional computers face fundamental limitation when solving problems that require evaluating an enormous number of possible configurations. To use a simplified analogy, solving such problems on a classical computer is like navigating a maze by checking one path at a time. Following a corridor until reaching a dead end, backtracking to the last junction, and trying to the next path until the exit is found. As the maze becomes more complex, the number of paths that must be checked grows explosively. In contrast, the quantum computer behaves as if it were exploring all paths at the same time, and then, through this processing, leaving only the paths that lead to the next exit. Because it can examine multiple possibilities simultaneously, it can drastically reduce the number of computer steps, enabling it solve far more complex problems than conventional computers. In fact, there are real-world problems that have remained unsolved due to the limitation of conventional computers. Examples including optimizing traffic and logistics in large cities, solving food problems by efficiently synergizing vitalities, designing optical drug molecular structures that are tailored to each person, and designing fusion reactors, which are expected to become new energy sources. Quantum computers are expected to make it possible to solve these kinds of problems. The source of this capability in quantum computers lies in a fundamentally a different way of representing information, namely through a quantum bit or a qubit. A conventional computer uses a bit that holds either 0 or 1 because a bit must be in one definite state at any moment. A classical system can represent only one state at a time. Quantum computers, on the other hand, use qubits that can hold both 0 and 1 at the same time. Since one qubit can represent two states at the same time, the number of states that can represent it grows exponentially as the number of qubits increases. By performing operation on these qubits, a quantum computer can process multiple states at once. The number of qubits a quantum computer processes directly determines the complexity of the problems it can solve. Systems with fewer than about 1,000 qubits are mainly used for research and development rather than practical applications. With around 100,000 qubits, it becomes possible to solve medium-scale problems. However, to use quantum computers broadly for applications with major social impact, between 1 million and 100 million qubits will be required. Next, let me look at how quantum computers have developed. The concept of quantum computing was proposed in 1980s. However, it took 35 years from that point to create a real quantum computer which only had 5 qubits. In recent years, advances in the semiconductor technologies and increased investment have accelerated the expansion of qubit counts. But achieving the same of the million or 100 million qubits is still a distant goal. One reason expanding qubit number is challenging is the limitation of conventional approaches. Superconducting and neutral atom systems require the extreme conditions such as ultra-low temperatures and vacuum environments, necessitating large, complex equipment. These requirements have been historically constrained the scalability of qubit count. In response, NTT has focused on the optical quantum approach, which has fewer operational constraints and is actively pursuing research and development in this area. Optical quantum computers offer advantages not present in conventional approaches, including operation at room temperature and atmospheric pressures, high speed and low power consumption. By leveraging the optical technologies cultivated through our communications expertise, NTT can achieve exceptional scalability, enabling rapid expansion of qubit counts. We have applied our long-standing optical technology research to create quantum light sources, generating light pulses with quantum properties. And in collaboration with OptQC, RIKEN, and others, realized an optical quantum computer in 2024. The latest result of this optical quantum computer research are on display on this event. And we encourage you to take a closer look. As mentioned earlier, NTT quantum light sources can generate light with exceptionally high-quality quantum properties. In other words, the quantum yield is high, which contribute to further improvement of scalability. This capability in the technology we have developed through advancing optical communications, including optical amplifications and modulation of light properties. As some of you may already know, NTT and OptQC have signed a partnership agreement aimed at the development of optical quantum computers. By combining NTT's optical communication technology applicable to the quantum field with OptQC development technology, for optical quantum computers, we aim to realize world-leading, scalable, and high reliable optical quantum computers. Even at the current forefront of global research, a qubit count remains in the 100 to a few thousand, far below the 1 million to 100 million qubits required for general purpose use. NTT aims to leverage the scalable nature of optical quantum system to achieve 1 million qubits as a world-leading level by 2030. Furthermore, we plan to take the lead in researching 100 million qubits in the future. Finally, as I presented, NTT is using optical technology to break through the limit of energy consumption and conventional computational processing, driving innovation in computing. The world is currently undergoing unprecedented transformation driven by AI. And NTT not only provides the infrastructure to support the AI era, but also contribute to the sustainable future through innovation in computing for the forthcoming quantum era. We sincerely hope you will look forward to NTT's future endeavors. Thank you very much for your kind attention. Thank you so much. Thank you.